Now that we have an operational definition of a reference frame, and that operational definition includes three orthogonal vectors, let's put this into practice. Let's take a position vector and let's define this using basis vectors from multiple reference frames. Let's start out by creating a reference frame A. And here we see our reference frame. Reference frame A has an origin at point O and is defined by the basis vectors A1, A2, and A3. Now let's define a point P that lies within this three-dimensional Euclidean space, and then there's a position vector that will define the position of point P, R of P with respect to O. And so now we quantify the position vector from O to P using a scalar magnitude applied to each of these directions, A1, A2, and A3. And so our position vector now is R, P with respect to O, is equal to some scalar dimension, we'll call it A sub 1, in the A sub 1 direction, plus a scalar A2 in the A sub 2 direction, plus a scalar A3 in the A3 direction. Each of those scalars are the distance that you would travel in the A1, A2, and A3 directions. And you can see also that each of these combinations of magnitude and direction each make up a vector itself. And so we would have a distance A1 in the A1 direction, a distance A2 in the A2 direction, and a distance A3 in the A3 direction that define the position vector R of P with respect to O. Now think back to our initial discussion on vectors. We said that vectors exist whether we like it or not. So this vector, position vector of P with respect to O, or the vector from O to P, it exists and it's up to us to define it. And so we've chosen to define it here with the basis A1, A2, and A3, and we come up with these three scalars, A sub 1, A sub 2, and A sub 3, to define the position vector R of P with respect to O. Now we can define this position vector of P with respect to O in any basis that we'd like. So let's add one more basis and one more reference frame. And we'll call this reference frame B. We'll keep the same origin, but we'll define three new basis vectors, B sub 1, B sub 2, and B sub 3. And we'll make this new reference frame B a reference frame that maintains the same plane as A1, A2, but is rotated within that plane, and then B3 and A3 will be the same. And so now using our new basis, in which we have a B1, a B2, and a B3 basis, we can define the same position vector, R, P with respect to O, as a distance B1 in the B1 direction, plus B2 in the B2 direction, plus B3 in the B3 direction. And so to illustrate what these distances look like in our new reference frame, is we would have the distance B1 in the B1 direction, we'd have the distance B2 in the B2 direction, and then the distance B3 in the B3 direction, and all this would be added together to give us the very same position vector, R of P with respect to O, and these two are still equal to each other, despite being defined in two different bases that are attached to two different reference frames. Another way to write this, then, is that our position vector, RP with respect to O, defined in the basis A, is going to be the set of scalars A1, A2, and A3. And remember, by putting this subscript of the reference frame, we're essentially saying what basis we're defining this vector in. And so similarly, the position vector P with respect to O, as defined in the B basis,
will be B1, B2, and B3, all scalar magnitudes, and then we indicate the reference frame, B, to say that this is the basis that we're defining it in. Now notice that A1 and B1, A2 and B2, and A3 and B3 are not necessarily equal to each other. They're dependent on the basis vectors that we're defining. And as we've written them here, A1, A2, and A3 are the Cartesian coordinates, A1, A2, and A3 in the A1, A2, and A3 directions. And so with these concepts in mind, I encourage you to look at examples 3.2 and 3.3 in your book, which the authors lay out these concepts for a pendulum position and then also satellite tracking.